Hello students. In this video, I'm going to discuss about different kinds of barometers, the history behind barometers, how do a barometer used to work, and what are the various uses of barometers. So let's start. As we know, a barometer is a simple instrument which we use to measure the atmospheric pressure. There are various kinds of barometers, but broadly we can classify them into simple barometers, 14th barometers, and aneroid barometers. Out of this, a simple barometer and a 14th barometer is also called as a liquid barometer because it used to have mercury in it, whereas an aneroid barometer is a dry barometer. The very first form of barometers was a simple barometer. It had been developed by a scientist called Torricelli in the year 1643. Let's understand with an animated video what is the history behind this barometer, which we had used for the first time to identify the atmospheric pressure.
Aristotle famously said, "Nature fears of empty space," when he claimed that a true vacuum, a space devoid of matter, could not exist because the surrounding matter would immediately fill it. Fortunately, he turned out to be wrong. A vacuum is a key component of the barometer, an instrument for measuring air pressure. And because air pressure correlates to temperature, and rapid shifts in it can contribute to hurricanes, tornadoes, and other extreme weather events, a barometer is one of the most essential tools for weather forecasters and scientists alike. How does a barometer work, and how was it invented? Well, it took a while. Because the theory of Aristotle and other ancient philosophers regarding the impossibility of a vacuum seemed to hold true in everyday life, few seriously thought to question it for nearly 2,000 years, until necessity raised the issue. In the early 17th century, Italian miners faced a serious problem when they found that their pumps could not raise water more than 10.3 meters high. Some scientists of the time, including one Galileo Galilei, proposed that sucking air out of the pipe was what made water rise to replace the void, but that its force was limited and could lift no more than 10.3 meters of water. However, the idea of a vacuum existing at all was still considered controversial, and the excitement over Galileo's unorthodox theory led Gasparo Berti to conduct a simple but brilliant experiment to demonstrate that it was possible. A long tube was filled with water and placed standing in a shallow pool with both ends plugged. The bottom end of the tube was then opened and water poured out into the basin until the level of the water remaining in the tube was 10.3 meters. With a gap remaining at the top and no air having entered the tube, Berti had succeeded in directly creating a stable vacuum. But even though the possibility of a vacuum had been demonstrated, not everyone was satisfied with Galileo's idea that this empty void was exerting some mysterious yet finite force on the water. Evangelista Torricelli, Galileo's young pupil and friend, decided to look at the problem from a different angle. Instead of focusing on the empty space inside the tube, he asked himself what else could be influencing the water. Because the only thing in contact with the water was the air surrounding the pool, he believed the pressure from this air could be the only thing preventing the water level in the tube from dropping further. He realized that the experiment was not only a tool to create a vacuum, but operated as a balance between the atmospheric pressure on the water outside the tube and the pressure from the water column inside the tube. The water level in the tube decreases until the two pressures are equal, which just happens to be when the water is at 10.3 meters. This idea was not easily accepted, as Galileo and others had traditionally thought that atmospheric air has no weight and exerts no pressure. Torricelli decided to repeat Berti's experiment with mercury instead of water. Because mercury was denser, it fell farther than the water, and the mercury column stood only about 76 centimeters tall. Not only did this allow Torricelli to make the instrument much more compact, it supported his idea that weight was the deciding factor. A variation on the experiment used two tubes, with one having a large bubble at the top. If Galileo's interpretation had been correct, the bigger vacuum in the second tube should have exerted more suction and lifted the mercury higher, but the level in both tubes was the same. The ultimate support for Torricelli's theory came via Blaise Pascal. who had such a mercury tube taken up a mountain and showed that the mercury level dropped as the atmospheric pressure decreased with altitude. Mercury barometers based on Torricelli's original model remained one of the most common ways to measure atmospheric pressure until 2007, when restrictions on the use of mercury due to its toxicity led to them no longer being produced in Europe. Nevertheless, Torricelli's invention, born of the willingness to question long-accepted dogmas about vacuums and the weight of air, is an outstanding example of how thinking outside of the box, or the tube, can have a heavy impact.
Now, let's see some of the things which you need to remember. Advantages of using mercury as a barometric liquid. As you know, the density of mercury is greater than any other liquid. Thus, only 76 centimeter of mercury column is needed to balance the atmospheric pressure. The vapor pressure of mercury is negligible. The mercury neither wets or sticks to the glass tube. The surface of mercury is very shiny. It is very easily available in its pure state. Defects related to simple barometer. There is no protection for the glass tube. Impurities may fall and mix with the mercury. It is very inconvenient to move from one place to another. The scale cannot be fixed with the tube to measure the atmospheric pressure. 14's barometer. You can say that it is a compact set of the simple barometer because here also we have mercury, but it is not open. It is enclosed in a rubber tube, as well as the glass container also been framed in a wooden plank. Let's understand its working and its construction with an animated video.
14's barometer. It is an improved form of barometer constructed and used in the laboratory. It consists of a cistern of mercury. The mercury level can be adjusted by means of a screw S provided underneath. A brass tip is fixed above the mercury level, which coincides with the zero of the scale of the barometer. A narrow glass tube filled with mercury is inverted and inserted in the mercury in the cistern. Adjusting the screw S, the mercury level can be made to coincide with the tip T. The reading of the mercury level M in the tube gives the atmospheric pressure. A vernier is also provided for accurate measurement of the reading. We can measure the atmospheric pressure accurately with 14's barometer, but it cannot be shifted casually from place to place. So, it is used as a standard barometer.
Through the video, I hope now it is very clear to you all that how a 14's barometer used to work. There are some main advantages of 14's barometer over a simple barometer, such as it is portable in use, as well as it gives us a very accurate reading. Now let's understand Aneroid barometers. Aneroid barometer is a dry barometer because there is no liquid in it. How it used to work and what is its construction, let's understand with an animated video.
The word aneroid means without liquid. The aneroid barometer is so named because it does not use any liquid. Let's look at components of an aneroid barometer. An aneroid barometer uses a small, flexible, partially evacuated metal box called an aneroid cell. The top surface is made of a corrugated metallic sheet and acts as a diaphragm. The metallic box expands or contracts in accordance with the changes in the atmospheric pressure. The resulting movements of the diaphragm are magnified with the help of a system of levers. The central lever of the system of levers is fixed at the middle of the diaphragm. One end of the central lever is connected to a spring. The spring prevents the evacuated metallic box from collapsing. The other end of the central lever is connected to the other levers of the system. The system of levers is further connected to a chain that passes over a pulley. A pointer that moves over a calibrated circular scale is attached to the pulley. The system of levers, the chain and the pulley helps transfer the motion of the diaphragm to the pointer on the circular scale. A hairspring is attached to the pulley to bring the pointer back to its normal position. The circular scale is calibrated to note the reading of atmospheric pressure directly. Let us now study the working of the aneroid barometer. Small changes in external air pressure cause the cell to expand or contract. This expansion and contraction drives the levers such that the tiny movements of the diaphragm are amplified and displayed on the face of the aneroid barometer. If the atmospheric pressure increases, it pushes the diaphragm downward. The motion of the diaphragm makes the central lever move in the downward direction. This small motion of the central lever is magnified by the system of levers and the metallic chain is pulled. The metallic chain, in turn, rotates the pulley and makes the pointer move on the scale. Since the scale is calibrated, the atmospheric pressure can be directly noted. When the atmospheric pressure decreases, the metallic box expands and the chain across the pulley loosens. The hairspring connected to the pulley helps the pointer adjust itself to the new atmospheric pressure. Aneroid barometers have some advantages over liquid barometers. An aneroid barometer is light and portable and can be fixed in any plane. It is calibrated to read atmospheric pressure directly. No prior adjustments are necessary. An aneroid barometer does not contain any liquid, and hence there is no fear of the liquid spilling over.
Here you can see some of the very basic uses of an aneroid barometer. It is used to measure the atmospheric pressure. It has also been used to make weather forecasts, as well as in aircrafts it has been used as an altimeter.